could be small, and also agents, bidders can be strategic, can act strategically. And then the other issue, we will soon realize that for this market, there's no standard valuation equivalent in the sense that the price of any bundle might not be the linear price anymore. So that means the price of a bundle is not necessarily equal to the sum of each individual price in the bundle. So here there's another problem, namely, if you have multiple sellers, then because the price are not separable, how to divide the profit among sellers is also an issue. But for the moment, we just focus on one seller. Actually, in the paper, we talk about how to deal with multiple sellers. Actually, we use the sharpening value to divide the profits. Okay. Okay, sorry. Okay. Okay, so here we consider all atoms are complements. So in the sense, atoms can create synergies. As a matter of fact, synergies are the major sources of revenues for many firms. Now here, we can give a number of examples to show such cases, like in particular different segments of transportation, telecommunication, pipelines, and also the other example is about different volumes of a book and different parts of a machine or equipment. So those are typical examples. Here we try to clarify the scope of the problem and some of the compromise. Then the other one, we have to explore a proper solution concept for this model. Then, okay, the last one is to develop an efficient and also strategy proof dynamic auction for this market. So as a matter of fact, after we finished the paper, so some people I think told us that actually we solved the first open question in a survey paper by the Maskin. But initially we started this problem basically due to the problem mentioned by Paul Milgram in his JPE 2000 paper. He talked about the general problem of complementarities, and then we had the first paper for this morning, that paper. But later on, we realized actually when all goods are complements, then that even just the three atoms you create, we will have a different scenario, different situation. So in this in his survey paper, actually his first question is about precisely what we try to solve. So how to design a dynamic auction for selling multiple complements. And then he proposed a number of open questions. I think some problems have been solved. Okay, so I should mention there are packaging options such as the one proposed by Oscar Milgram. Those options can apply to more general developments, but they have to use a discriminatory pricing rule. It means that for the same bundle of goods, different people have to pay different price. So, but of course, in practice, people are more used to anonymous price. And even in some countries, if you go to any shops, actually, you cannot use, you cannot say any discriminatory prices. However, discriminatory and non-linear pricing, is quite common and also quite natural when a seller is independent and separately negotiated with several buyers. So okay, let's look at the model. So we have just one seller for the moment. We have to think about. So we have n indivisible goods, and we have n potential buyers. Okay, we use 0 to represent the seller, and then each agent has a utility function of goods. So this is of course, when you have no goods, then the value is 0. Okay. So here we have some assumption. As in the morning, I assume that all valuations is measured in currency, in units of currency, so integers, and then every agent has a quasi-linear utility in money. Okay, so then we have the third assumption. It's about super additivities, actually for this is for all agents, not necessarily just bidder, but for all agents, include the seller and the bidders. So this means that if you have two disjoint sets of atoms, then you use the two bundles together is more valuable than you use them separately. So this is the most general form of complementarity. Okay, then some special cases we can think about is a supermodule than this one. So the supermodule means the marginal marginal value of atoms is increasing. And you also have a kind of a gross components. So increase the price of one atom will decrease agents' demand for other atoms. So this is the so you say the assumptions are quite very clean, very simple, and also in some sense it's very easy to check. This is a very simple condition. Okay, now we talk about efficient allocation. And so allocation, just a partition of goods among all agents. So it's possible that some atoms might not be sold, then just the seller will keep it. Okay, efficient is allocation is efficient if this achieves the highest social market value. Okay, then the first question is that whether they exist standard variation equilibrium. The standard variation equilibrium means that the price is linear. If you have a bundle of goods, then the price you pay for the bundle is equal to the sum of every item's price in the bundle. Okay, let's look at one very simple example. So here we have 3 items A, B, C, and we have 3 buyers, 1 seller. Okay, look at this table. You see the value of, just look at the first one, the value of a single item A is 2, and single item B is 2, C has no value, but A, B together, they create a synergy, so the value is 7, and AC is 3, so also more than you use them separately, BC, okay, BC also, okay, ABC. All items are complementary to each other. And bidder 2 has a similar pattern, but slightly different. Shift the focus. And bidder 3 also okay, has similar pattern of values. Then the seller also regards all items as complements. Okay, for this example, we have 2 efficient allocations. So namely, AB, you have AB together and give this to, if we know this value, of course, then you should give AB to bidder 1. And C, you can either give it to bidder 2 or bidder 3. So this will be efficient allocation. However, I claim that neither of this efficient allocation can be supported by a linear price. So DA, DB, DC. Okay, let's look at the first efficient allocation A, B, and C. So now I claim that this cannot be supported by linear price, BA, PB, PC. Okay, so look at so look at the if the price can support this one, so this means this you take AB will be optimal for bidder 1. So let's see. So this means that 7 minus PA, PB should be greater than you take loss, right? So this is then for the second bidder. So second bidder, take C is optimal. So therefore, 2 minus price should be greater than or equal to you take loss. And then take C is optimal. So then you compare with the other case, you take A, C together. So then this should be true. And from here, you immediately have that PA, the price should be no less than 4. Okay, then for bidder 3, so the empty is optimal. So take loss is optimal. So then, so this 0 should be greater than or equal to 2 minus PC. And then, of course, take losing is optimal, so then it should be no less than or equal to when you take BC together. Okay, now here notice that this one is less than or equal to 2, and here is greater than or equal to. So therefore, the price of C should be equal to 2. Then from here, we immediately know that this price of B should be no less than 4. Okay, you combine this together, this one and this one together, then the value should be no less than 8, which contradicts this equality. So this shows that indeed there's no standard variation equilibrium when all goods are complementary to each other. So as long as you have just 3 atoms, but 2 will be loopable.
Okay.
Yeah.
How about 2 meters? Is an example is 2 meters?
2 meters, if you have 3 atoms, you can still have a problem. 2 meters, 3 atoms. If 3 atoms are complementary, you might not have a variation equilibrium.
Even with 2 meters.
Yeah.
I mean, this particular construction seems to depend on there being 3 meters, but
Yeah. I think I believe that if you have 2 meters, 3 atoms, you can still have a counterexample. Yeah. Okay. So from this example, we know that we cannot use the standard variation equilibrium anymore. Then we think about whether it's possible. We still have anonymous, but now the price might not be linear anymore. So we think about a nonlinear pricing rule. So here now we define the price in such a way. So for any bundle, we give a price, and this price is the same for every agent. Then for any unsorted atoms, the price should be equal to the reserve price of the bundle of the seller. Okay, then the linear, if the price function is linear, then this means that for any bundle, for any bundle, then the price of the bundle should be equal to the you add up all individual price in the bundle. So here in this auction, so we will show that actually there exists anonymous nonlinear pricing system to support efficient allocations. Okay, so let's look at the demand of every bidder. So this is a standard one, but now the price is not additive anymore. Just for any bundle, you have a price. Now we need to think about what will be the business strategy of just consider the point of view of the seller. So seller actually think about all possible partitions of bundles which can give her the highest revenue. So here you see now we all possible partitions of the goods. So then here we take the maximum the number of items and the number of bidders. This is quite important because the seller just consider about what will be the best possibility to achieve the highest revenue. So then we use L. So zero means that the atoms should be kept by the seller. And then the other one, just the market price. So here I use a IJ L is a partition of all goods among members in L. So this is not necessarily agents anymore, right? So it could be agent. So now I use a paragraph B to represent the family of all such partitions. Then what is the problem of the seller? So the seller just tries to maximize her revenues, and then her supply family will be the collections of such pie which maximize the revenues of the seller. Okay, we are interested in this case, if this happens, that a supply set pie in this one is allocation, okay, exactly, and this should be equal to the assignment of among all agents. So this is something we want to have. So now we can define the the anonymous nonlinear pricing valuation equilibrium. This has two parts. One is the pricing function P star, and one is the allocation pi star, such that this pi star should be in the supply set of the seller, and then every bidder should get his optimal bundle. So this is the equilibrium concept we use. Okay, so here just notice that this is in the sense here I have to we have to be cautious in the sense that this option actually you cannot use it online, because it's possible that you see here by the definition that in any this IV or any sold bundle, we always have this this relationship for any two disjoint sets of bundle. So the price of the bundle together, S and T, is no less than you add them zero. So in retail market, you cannot have such a relationship.
So T and S are two disjoint sets in set B.
Yeah, B is a sort. Yeah. So only in auction house, when all people come together, then you cannot manipulate just for this pricing rule. So you have to come. Real people have to come together in the auction house. Therefore, there's no possibility of because it's a nonlinear pricing rule.
Why is it? So if
So-
this kind of thing should be true for any partition of B, then I understand.
Yeah.
But why for any B?
So here it's possible. So just imagine if I don't know your identity, right? You might actually you want to have B, right?
Yeah.
You want to have B.
So if
But-
S and T forms a partition of B,
Yeah.
this should be true. But
Yeah, then you don't pay
yeah,
pay
if
this
S and
price.
T form a partition of B,
Yeah,
then
yeah.
that's
So you don't pay that price.
yeah, but it's different, right? So
No, no.
SRT must be S cup T might be strictly smaller than P, B.
So here you see, I talk about this equilibrium. So in equilibrium, you have everyone gets the optimal bundle, right? However, it is possible that the price you pay the bundle S and T together may be strictly greater than two separate bundle. So you might, if I cannot check your identity, so you might say, I want to S. You pretend to be one person, and the another person also buy for you. Then actually you don't need to pay this price. You pay them separately. So maybe sorry, let me explain again. So actually now you want to buy bundle, right? B, bundle B.
Buyer, seller?
Yeah.
Buyer.
No, buyer. You are buyer.
Oh, okay.
You are buyer. You want to have you want to buy bundle B.
Yeah.
But the price of bundle B could be strictly greater than this two separate, the price of two separate bundles. If I don't know your identity, you might just buy this separately.
Yeah, that's so true, but that has nothing to do with the statement here.
Oh.
Inequality holds because of sellers.
Yeah. So this is what I mean that so for this pricing rule
That's a problem.
has a problem. Namely, we need to have all people, all buyers together. I can check the identity. They cannot manipulate this pricing rule. This is what I'm trying to say.
Oh, okay, go on.
Okay. Okay. So here we have a first okay, a very simple proposition. So okay, if it's this price equilibrium or relation equilibrium, then this pay star is efficient also for any equilibrium price function and any efficient allocation. Then you combine them together, you will make a new relation equilibrium.
Assuming that commodities are complements.
Yes. This one. This one we use it. Yeah. This one we use it.
So does it carry over to other wider cases, nonlinear pricing?
That will be true. That will be true.
Maybe nonlinear and personalized price supports allocation in any general case. But you don't have anonymity here, so it's not absolutely clear. This carries over.
If it's nonlinear, I'm not quite sure. Oh no, if it's a discriminatory price, I'm not quite sure. That's why I'm not quite sure.
Technically, proposition one is proved for complements.
Yes. Yeah. Okay. So the other question you might think about is whether this anonymous nonlinear pricing equilibrium could be too general to be interesting. This is also an issue we may think about. So actually, we have an example. This example was due to Vivian, Quincy, Martini, Quincy, Silver. So in the paper, they actually try to give a kind of a utility function which satisfy gross substitutes complements. And they give an example of this. Actually, every Bedel's utility function satisfy substituted is a submodular function. So this one, all utility functions are submodular, and there's no standard variation equilibrium for this example.
So are the substitutes here?
No. This is sorry. It is, yeah, substitutes. Okay. Yeah, sorry. It's a substitute. And actually, there's only one unique efficient allocation. So B is assigned to beta 1, and A is given to beta 2, and C is given to beta 3. So this is the unique efficient allocation. So because there's no variation, no standard variation equilibrium, you may ask whether there's any nonlinear, anonymous nonlinear variation prices to support this.
Question: if a goods are substitute, variation equilibrium should exist.
So when you have a M natural concave function, that it is true.
But you just proved that it's equivalent to M natural concavity, substitutability.
No, this is not a gross substitute. This is in general sense it's a substitute, but it's not in precise sense of gross substitute. Sorry, this could be confusing the language.
So this is not the quasi linear model.
It's quasi linear.
Then there's no difference between gross and net, because there's no income effect.
No, so here submodular. This
module is somewhat different from substitute.
Exactly.
Okay.
Exactly. So here I just claim that this function is submodular, but it's not
natural.
It's not natural. Sorry.
It's not the substitute.
Yeah.
Okay.
It's not
Okay.
substitute.
Good.
Yeah.
I got you.
Yeah. So okay. So what I can claim for this example, you even don't have anonymous nonlinear variation equilibrium prices to support this unique outcome. Why? Okay. Suppose we can use we have a bundle package price. So for this one, in order to have a nonlinear price, then the seller might set the price of the bundle AB in such a way that this price is greater than, strictly greater than you sell them separately. So then the seller will choose which one? The seller will choose this bundle together and the C. So but in this case, now this pair is not in the supply side of the seller, right? So you can do this exercise for any two combination of goods, so BC or AC, in such a way that this this pair will not be in the supply side of the seller. So as long as you have such situation, then there's no anonymous nonlinear variation prices to support this unique efficient application. Is this clear? Yeah. because the idea is that seller always tries to maximize whole revenue, and in order to have so because this example, it's already known that there's a low linear price valuation equivalent prices vectors to support the efficient allocation, right? So you need to create non-linear pricing rule. So what is the non-linear pricing rule? The possibility is that you might have a ABC together. ABC together, then the price of ABC must be greater than any other combination. But when you have ABC together, the seller will choose ABC. Then, but the unique outcome is the unique efficient allocation is pi. So then pi can never be in the supply set of the seller. So this is why we cannot have a anonymous nonlinear pricing rule to support this unique efficient allocation. Okay.
So therefore, sorry. So if this strict inequality is equality, so P of AB is equal to P of A plus P of B. So then, what's wrong with?
You can also have that, but still it's not. You cannot. But then if it's equal, right? If it's equal, then it's linear.
Right.
So they already proved that there's a low linear.
Oh, I see. So you're saying that if this is holds as equality, so then the price is linear. But so you already proved that there is no.
They prove it. They prove that there's a.
So there's no.
Yeah.
So as a result, okay.
Yeah. Is this clear?
I think so. Yeah.
Yeah, because these three already proved for this example. There's no standard variation equilibrium.
Right.
So as long as you have a equality, so return to the case. And so in order to have a nonlinear, then you have to have a strength.
I see.
Yeah, that's
If you allow personalized nonlinear price, does it exist?
I think so. I think so.
The seller's problem.
Yeah. I think if you allow nonlinear price, personalized price, this must exist.
So one easy way for consumer side is what I'm supposed to consume at the equilibrium allocation is not so expensive. Everything else is very expensive.
Yeah, exactly.
But if that is true, seller would not choose the bundle. Yeah, I am choosing. So it's not immediately clear if
for personalized discriminatory problem, that you can have such system to support this efficient allocation.
Oh, really?
Yeah. Okay, so we can prove that the market under those three conditions, we can have anonymous nonlinear pricing or variation equilibrium. So now we will introduce the function which actually will generate such equilibrium outcome. Okay, now let's do the exercise. Okay, what is sincere bidding? So as long as every time that the bidder reports actually one of the optimal bundle at the current price PT, but when the empty is also optimal, then this person should report the empty set. This is and here, sorry. Here, I just want to mention, point out the difference between this model and the previous models, previous auctions. So in the previous auctions, like demand gears Tomeyer, the auctioneer actually requires every bidder to report the entire demand set. Here, it's quite interesting that we just need the auctioneer just needs every bidder to report a single optimal bundle, and but this has to be used that if the empty set is your optimal bundle, then you should report the empty set. This is one thing which is useful. Okay, then how we define what we mean over demand set. So given a price function, so the seller will report a supply set. Okay, again, that as I mentioned in the previous lecture, I talk about that the seller is always honest. So only bidders can be strategic. Seller is always honest. Okay. So then basically the seller report. So first we have the price function. Then the seller reports a supply set with respect to this given function. Then every bidder reports a demand bundle BH, just one demand bundle, optimal. Okay, so with respect to this supply set pi and the reported optimal bundle by every bidder, then we say that a bundle B is over demand if it's demand by more than one bidder. So this is a standard one. However, there's another one which is not standard, but it's still quite a large one, is that demand by some bidder could be just one. That but her demand bundle, I should not use her, his, because the seller is she, and okay, his bundle is not in the seller's supply set. So this is a very important point. So some bidder report an optimal bundle of his, and even if this bundle just demand by one person, but his bundle, optimal bundle, is not in the supply set of the seller, then we also say this bundle is oversupply, or over demand, sorry, over demand. So this is
So here in this definition, so over demandedness is defined with respect to bundle, right? So for example, so suppose a bundle B consists of two items, 1 and 2. And so suppose that 100 buyers demand bundle 1, and 100 buyers demand item 2 alone, right? But in this case, so bundle 1, 2 is not over demanded. Is that correct?
But it's over demand. You see here, as long as two bidders demand the same bundle, then this bundle is over demanded.
Right. So here, so 100 bidder demands item 1 alone, not bundle 1, 2. Okay. So let's check whether bundle there's over demand in bundle 1, 2. Okay.
you see here, this bundle means the same bundle for more than one bidder, right?
Right.
So you and me reported this optimal bundle.
Right.
So the same bundle,
Uh-huh.
if there are more than one, so now it's two. If two of us demand this bundle,
Uh-huh.
then this bundle is over demand.
Demand. Okay.
Yeah. The more interesting case is this case. Only myself demand this bundle, no one else demand. But if this bundle is not supplied by the seller, then this bundle is also over demand. So this is quite pretty new. Yeah, and this is not did not exist before this paper. Okay. Okay. Now we have auction. Now this auction actually is quite easy to understand. And so basically the auctioneer initially announced a pricing function such that so just the price of every bundle equal to the reserve price or even below is okay. So then at each round of the auction, then every bidder reports a demand bundle, just one bundle. Of course, as we required previously, if the empty set is an optimum bundle, then you are asked to report the empty set. Then the auctioneer chooses a supply set, pay T, so that the market list over demands set. Oh, this actually is not necessary. This is not necessary. Just choose one supply set is enough. This is just what we want to we want to speed up. This is not necessary. Just okay. The auctioneer choose a supply set is enough. Not this part. Okay. So if low bound is over demand, then we go to step 3. So basically, the auction will stop. If there's an oversupply set, supplied bundle, then we increase the price of every over demand bundle by 1 unit, and do not change the price of any other bundle. And then, so in the last step, so this one, say the auctioneer assigns the bundle when the auction actually stops, assigns the last the bundle to every bidder, and they ask them to pay the current price. This is the standard one. Then what is not a standard is that in addition, for any non-empty bundle which is supplied by the seller and which is not demanded by any bidder. Okay, then we have 2 cases to consider. If the bundle, if the price of the bundle, the bundle S, this S, the price is equal to the reserve price, then the seller just keeps it. Otherwise, this one is very important. Otherwise, the auctioneer can assign this bundle to some bidder who previously demanded this bundle, but was the last one to give up this bundle because the price has increased. Then this bidder might switch to demand other bundle. So then, if we have such a bidder and we have such bundle, then this bundle should be assigned to this bidder and ask him to pay this price, the current price, the last price. So this is what we call complementarity activity rule, and this is a quite important one. And so this rule is quite essential.
Maybe I may not have understood the auction rule, but
Yeah.
so how can you exclude the possibility in which the same bidder is assigned some bundle
Yeah.
according to this first sentence?
Yes.
And that person is simultaneously assigned some good because of the last part of this auction.
Yeah.
So
So this is a very interesting case. So we will show it's optimal. It's still optimal for the bidder, for this bidder who is also assigned this bundle together with BH.
also that bidder gets both BH or T and this
As
bundle he
Yeah.
gave up.
We will show actually this will be still optimal
Okay.
for the bidder, for this bidder to take it.
Okay.
So that's actually really important. So what we call this rule is a complementary activity rule.
I'm confused.
Yeah.
If bidder H consumes a union of B and S, then isn't he supposed to pay P of B union S?
That's right.
But in this auction, he's paying something different. P of B plus P of S. So
Yes,
that turns out to be equal.
you are right, but we will show
Okay.
this rule works.
Okay.
Yeah.
Okay.
So this is quite important. So first, maybe so you can understand that because the price of every bundle starts from the reserve price, right? So when the price is above the reserve price, it means this bundle must have been demanded by some bundle or some bidder. Sorry. That's clear, right? So then if at the last step, when the auction stops, when there's a low over demand, but such bundle is not demanded by anyone, then because by our pricing rule that any bundle, if the price is above the reserve price, then it has to be assigned to some bidder, because otherwise we cannot have a variation equivalent price. So this is something we have to prove. Okay. Okay, so let's look at this example, and I already distributed the example. Let me show you this.
Sorry. So if some bundle is demanded at some point, and then it's possible that there is some other bundle that has the intersection with the first bundle, and this bundle will be sold, right? In that case, the first bundle cannot be sold anymore.
But then you see that the supply set is a partition of items, so that you cannot have such an intersection. Both bundles have non-empty intersection. We cannot have that one. So we have to prove that this case can be excluded. Yeah. Okay. So let me just show you this simple example, then you can get some idea about why this auction works. Okay. Okay, at the first step, just start the auction starts with the reserve price for every bundle.
So what's the each element of price vector? So one is
This is
A.
A, B, C, A, B, and AC, and
BC.
BC, yeah.
And everything together.
Yeah, then the last one, the ABC, I have to, I have to be more careful. Okay, this one. Yeah, A, B, A, C, B, C, sorry, yeah. Okay. Let me explain step by step. So you see here, AB is optimal bundle. If you check the example, and the AC is optimal bundle, A optimal bundle, and BC is an optimal bundle at this price. Okay, for the seller, what is the best combination or best partition of the goods so that she can have the highest revenue. So so A, B, C. So then this is one of the optimal yeah choice. Okay. Now look at here. Both AC, BC are not in this supply set. So that we increase yeah. So we increase the price of AC and BC. So this is this one. So this is AC, right? And this is BC. Okay, then the next step. And here, now, okay, this actually ABC. Now look at here, the seller takes AC is this one, right? 3, and B is 1, so 4. So this is optimal for the seller. The highest revenue for this price is 4 for the seller. Okay, then AB, AC, ABC, neither of them is supplied by the seller.
AC is supplied.
Oh, sorry. Sorry. So
AB and ABC.
ABC is not supplied, sorry, yeah. Okay, so then we increase the price ABC and AB. So ABC is this one, and AB is this one. Okay, then repeatedly we do. So here at this step, now, okay, now we have this optimal one, this optimal one. So now here you see ABC is not supplied, C is not supplied, and AB is not supplied. So then we need to increase the price of every such bundle. Okay, so you see now actually figure 2 switches his optimal demand, switches to A. Okay, then look at this step. So A, we need to increase the price of A, and we need to increase the price of A, B, C. Okay, then this step, we need to increase the price AC and BC. So AC, this one, and the BC is this one. Okay, now here, this step, now, so AB is not in the supply set, so we need to increase the price AB. So we have this one. Now, there's no over demand anymore. Okay, now look at the price of every bundle. Now you see the price of C, the current price is 2, right? 2 is above the reserve price. So according to the auction rule, the complementary activity rule says that we should assign any items at the last price, which is not demanded by anyone, but was previously demanded and was the last one to give up. We should assign that bundle to that bidder, and that bidder should pay the last price. So this means that C should be assigned to bidder 2, and bidder 2 should pay this price. And now you can see actually, so you see AB will be given to bidder 1. So bidder 1 pays the price 6, and then bidder 2 pays price 2. And that's actually, if you look at example, it's indeed optimal for the both bidders. So he's actually indifferent between taking one or not. Okay, now let's prove that.
Sorry,
Yeah, sorry.
and clarification of the how the sellers make the partition of the here. You're trying to say that the auctioneer chooses a supply set so that the market yields the least over demand bundles, but as
that one is not necessary. So that rule, I just give that rule in order to speed up the process. So in principle, the seller just can choose any set in her supply set.
okay.
Yeah.
I
Okay. Yeah. Okay. So
Going back to my question.
yeah.
So in another example,
Yeah.
you might assign bundle T and bundle S, which are disjoint to the same person.
Yeah.
And this person is paying the price of T plus price for S.
Yeah.
But isn't he supposed to pay the price for the union of S and T?
If it's in this auction, then he pays
union is
union.
equal to the
Yeah.
addition.
Yeah.
Okay.
Yeah. Okay. So I will prove that. So here, sorry. Oh no, it's okay. It's okay. Okay. So suppose that we have the all assumptions are satisfied. If all bidders bid sincerely, then this basic auction will generate anonymous valuation equilibrium price vectors. Okay, in finite number of steps. So let's prove that this how it works. So actually, the first one we can immediately understand why. I think it's okay. Disconnect. Oh. Yeah. Okay, so first one, because you see this process that the prices are weekly increasing, and the valuations of every bidder is finite. So the value is finite, so it cannot go forever. So it must be stopped somewhere. Okay, now let's use this P star. Okay, T star is the last last step of the option. Okay, let's this gamma star be the last supply set given by the seller. Okay, this is important to point out that by definition, this gamma star is a partition of all atoms that maximize seller's revenue. So now we will actually construct a I star so that this will form an anonymous and nonlinear variation equilibrium. Okay, so if at the last round that at this price P star, no bounder is, of course, the last one is no bounder is over demand because it has already stopped. So, of course, if for any bounder, if his demand bundle is not empty, it must be in the supply set. Because as long as it's not in the supply set, the price will have to increase, right? So when this auction stops, then every non-empty set, which is demanded by some bidder, that bundle must be in the supply set of the seller. Because otherwise, by definition, any over demand set the price should be increased. So this is quite important. Of course, I mean, if the union of all optimal bundles by bidders is equal to the n, then the sense is done. We don't need to worry about. But now there's other cases which is more important. Namely, sorry, I should move. So assume that there's some bundle which is not demanded by any bidder at the last step. So we call such a bundle a squeezed out bundle. First, we consider that the price is equal to the reserve price. Then basically we will put all such a bundle together and give that to the seller. And we need to prove that one. Namely, we need to prove that this union of such bundles is optimal to the seller. Okay, so now look at such the collection of such squeezed out bundles, which equal to the reserve price, but it's not those which are demanded by the bidders. Okay, this one. Now, so now we take such bundle must be disjoint, right? Because it's in the supply set of the seller, so it must be disjoint. Okay, now we consider the union of all such squeezed bundles. Okay, now we claim that we can assign this bundle to the seller. Okay, so first, this is obviously true because if it's above the reserve price, then there's another case to consider. Okay, so here notice that this we have to use the super additivity condition so that this will be greater than or equal to separate case disjointed. Okay, this is by assumption, so equal to each individual's price. Okay, now on the other hand, now because gamma star is maximizing the revenue of the seller with respect to price P star. So that this part has to be no greater than this part. So that if you look at this both sides, then actually this price is just equal to the union. You add up all squeezed bundles price together. So this is optimal for the seller to take. Then the other part is more important is about any bundle which is above the price is above the reserve price. So okay, let's consider one of such bidder. It's possible maybe previously two bidders demand this bundle and two bidders simultaneously give up. So if this is the case, we just choose one of the two randomly. That's okay. Okay, let T be the step in which bidder A still demanded, but will give up in the next step. This one T must be strictly before T star, right? This. Okay, then by the rule, we will ask bidder to take this bundle together with his demanded bundle, but we ask this bidder to pay the current price of this bundle B. Okay. So first notice that. Yeah.
So the bidder chooses the bundle that maximizes the surplus, right?
Yes.
Every time. And if there are multiple bundles that maximize surplus, then the bidder just choose one.
Yes.
So even if maybe bidder I may be the last person gave up.
Yeah.
Maybe the bidder J may be J could be demanding the same bundle that goes to because he was indifferent, chose a different bundle.
Yeah.
And they would give up if he demanded that bundle.
Mm-hmm.
Even in that case, you choose bidder I.
Yeah.
Separate. So
Yeah. Bidder A. Yeah.
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 So yeah.
So suppose I'm that person, that bidder. I answer at current price. I already demand something else, some other bundle. Now I'm asked to answer demand this bundle and to pay the price, the current price of this bundle. So now I will show actually when I have both bundles, it will be still optimal for me to take it. this is something we want to prove. Yeah. Okay. So here, so at the time t, so this value for the beta L for bundle B, the price must be the surplus must be greater than or equal to 1. Why? Because if by the auction rule, if it's 0, then the bidder should report the empty set. And because all values are integers, so this must be true. Okay. Or so then the last price, no, this price, the last price could be either, maybe I wait for yeah. Okay. So then at the last round of the auction, the price of that bundle either has not yet changed from step T or just increased by 1 unit. So this is the observation. So then for this bidder, so this will be true for when he taking this bundle independently. So at the moment I just focus on this bundle, but then now later on I will show together with this one and with the one he already demanded will be still optimal. Okay. All right, okay. Then move back. Yeah. Yeah. No, no. Okay. Now it's okay. Okay, so we are here. Okay, now. Okay, if this is the case, if we currently this guy does not demand anything else than just like a previous case, it's optimal. This is it's a simple case. Now we consider currently he demanded a different bundle. Now we will show this combination of 2 different bundles is will be optimal for him as well. So for the seller, we know this one. Okay, for the seller, we know this. Okay, this one, and for the bidder, now okay, bidder. So super additivity has this property, right? Because these 2 bundles are disjoint. So this must be true. Okay, now from the previous 3 and 4, 3 and 4, we have this one. So look at we consider whether it's optimal for beta L to have this union of 2 bundles. So this one, okay, this same, and this one, okay, you have this separately. Okay, then the last one. So the last inequality is derived from this let me put it back from this one, this one. Okay. Okay, so this one. Okay, now we have this one. So this shows that you have we have this one. Then we also consider this case. The last one actually just try to show actually the price for these two bundles is just equal. So actually for this video, he just pays sum up. So there's no strict inequality. So
where are we using the
sugar
fact that L is the last person to give up?
here. Sorry, I made a wrong step. Yeah, here, this factor, we have to use it. The last one, so it means that when you give up the bundle D, it means that your profit for this bundle should your surplus should be at least equal to 1.
Okay, so if L is not the last one, then okay.
Yeah, so this factor is used. Yeah. Okay, so then we can always use this argument for any such squeezed bundle. So then we get the FV. Okay, so I don't think I will have time for the other part, but the other part, in some sense, I will discuss in the third lecture. But of course, this is quite different actually from third part, but some general idea is similar about the incentive compatibility. So basically, that this incentive compatibility option has to use this basic option for all n plus 1 market. So that will be discussed in our next lecture. Okay, thank you. I stop here.
Okay, any question? Yeah, one question, is this a polynomial time algorithm?
Probably no.
Oh.
Yeah.
Related to this question, compared to the gross substitute market algorithm, which is faster? Intuitively, in nonlinear market, we need to decide price not only for individual goods, but also the combination of the goods. So
Yeah. This in a sense, this will be slow if you have too many items, right?
Yes.
Because it's to the power n. So you have so many combinations. Yeah, to the power n. Yeah, so it could be.
The size of price vector is not polynomial.
But
Already.
yeah. So this is why that when you have say personalized price of patchy auction, that you will be much more time consuming. Yeah. But I mean, the good thing is that for this market, we only have one non-linear pricing rule for all markets. Yeah.
Right.
Okay.
Any other questions or comments? Okay, thank you very much.
Okay. Thank you.
Next to Wednesday.
Yeah. The same time.
Same time.
Yeah. Okay. Thank you very much.
Yeah, thank you. そしたら教室を取って入りきらなかった。いいよ。そしたら、どっか共同研究室取っておこう。場所はメールで今日伝えます。はい。そうですよ。はいはい。
No, it's okay. Or you don't know. Sorry. I moved.
これが、
Oh, okay. Yeah.
まあ結構初見の回にはないでしょう。
Thank you. Thank you for many interesting questions. Yeah, 30 minutes. 30 minutes is not too bad. Yeah.
I have a question about in the lecture, use or any variations in the application.
Yeah.
Which minimize the net of how can usually I can divide it so that the dual program is
Actually, we don't use duality problem, so I think maybe and it includes the unit of demand. So all of this will be covered. So then you will. Okay. Okay. Good.
Thank you.
Yeah. Okay.
See you next week.
Yeah.
See you next week.
Yeah. Hi. Thank you for coming.
My answer by email.
Yeah. Thank you. So I was thinking.
I get this.
So I think.
これでミュート。
Okay. Yeah.
そしたらここが見こっちは。
So I was thinking that
みたいになって
yeah,
て、
はい。
赤くなってるのが切れてるですか。
あ、なるほ
we
ど。
have a very general market. So we have a number of tables.
マイクとカメラ両方使うのができて、普段はカメラでは入れてないんで、
And that one.
普段触らない。
So, but
だから、
of course,
マイクの絵がついてるけれども、マイクもカメラも全体が落ちるってことなのかな、これを押すとね。
the model.
落ちて赤く光ってる時っていうのは、カメラも、まあ、
The market, I love it. I like to have a mission to prevent more. So